So compression members, these are typically columns in buildings, which are vertical members. They resist gravity loads. That is the primary purpose of columns. And then you may have struts in trusses. So what is a strut?
Diagonal compression member.
Yes. So if you have a truss like this, then these intermediate members, they will all be called struts. This one, this one, this one, this one. And they have to be in compression for them to be called strut. Okay, so struts in trusses. Principal rafter in a truss. So this one, typically under gravity loads, these two members are in compression. So these are principal rafters. They are in truss. Boom in a crane. So when you have a crane, the boom of the crane, that is also a truss mostly. So even that is in, it may have compression components. Bracing struts or cross bracing. So when you have a bracing, again, bracing could be a typical building. You may have a typical regular frame, steel frame, and then you may have some kind of a bracing system. So these are braces, and they may undergo compressive forces. Right? So these are typically used in structures. So the behavior of steel, good thing is, unlike concrete, steel behaves very similarly between tension and compression. So the E value that you get in tension test, coupon tension test, the same E value is applicable in the compression test, in compression as well. So if I may plot it. Not Fy, sorry. Stress. So if this is the typical stress strain plot of steel in tension, what will be the stress strain plot in compression? Okay, I'll not draw beyond this because that is questionable. Okay. So this is tension side. So whatever E value elastic modulus you get, the same elastic modulus will be available in compression as well. Whatever Fy you get here, similar Fy values, same Fy value will be available in compression as well. You understand that, right? I'm plotting it on both tension as well as compression side. So on this side is compression, this side is compression, and this side is tension. Okay. Now what happens is that up to Fy, you can say that the behavior in tension and compression is similar, but then we don't go beyond Fy. We just stay up to here. But in tension, when we were designing, there were two limit states we were using. We were using gross cross-section yielding, right? And also we were using, the other limit state was net section.
Net section rupture.
Correct. So we were using these two limit states. And for net section rupture, we were not using Fy, but we were using the Fu value. Correct? But we don't do that in compression. We go up to Fy, and that is considered as a limit state. But once Fy is met or reached, then we don't go beyond Fy. We cannot take advantage of the strain hardening part. But up to Fy, the behavior in tension and compression is pretty similar. And in fact, if you have a compression member, the behavior of the compression member in tension and compression is pretty similar to the coupon behavior. So if I have a column, okay, there are some differences that we will talk in a minute. But in general, you can say if I have a column versus if I take a coupon that is cut from the similar steel as this column. So this is a coupon that is cut from a column like this. And if we do the tensile test on this coupon and we get this part of the curve stress strain, and then subsequently we take this column, okay, not a very long one. We take this column and we apply compression on this. we will get similar stress strain plot as similar to this. Okay. Similar plot as this one. Agreed? So the member behavior, as long as member is loaded uniformly, member behavior is very similar to the coupon behavior or material behavior. So this is a material test, this is a member level test, but the behavior is very similar if we plot stress versus strain. Okay? And plus tension and compression behavior is very similar. That is up to Fy. But beyond Fy, what happens is what we need to discuss. So in tension, we can utilize up to Fu in certain cases, in some limit states, but not in some limit states. But in some limit states, we can utilize up to Fu. In compression, we can never do that. And I want somebody to answer. Can I call you by names and check if somebody can answer? Or you want to, I think it's not covered yet, so I'll give anybody who wants to answer a chance. Okay, try. Why don't we go beyond Fy in compression?
So because of buckling.
Buckling of what?
Because of buckling.
Buckling of like why buckling? Where does the buckling come into picture?
So because
We are talking about crushing. Go on.
So because if we apply load, then the load find the low resistance path to pass. That's why it got buckled beyond Fy.
Can you repeat? I didn't follow you. Sorry.
So if we apply compressive load on the member, then then its position is downing axially, and at a certain point it got the shortest path.
No. So let's say we take a small column, a stub column. Okay. So there is no it's not susceptible to buckling as such, or elastic buckling as they call it. Actually, buckling is the right answer, but I don't know whether.
It depends upon the.
One second. Lohit was trying before. Yeah, Lohit, tell us.
Sir, it depends upon the boundary condition and the length of the member. Maybe after the Fu, after Fy.
No. I think Aditya was on the right track, but he just didn't use the right words, I suppose.
It buckles locally, sir. The yield, when it yields, it buckles locally at that point.
Why does it buckle locally?
Because there's no, it can't stretch. While in the tension, it can stretch. It can take its ductile character, but in the compression, it can't. It can't move. So it buckles.
Yeah. I mean, I know that you guys are. I mean, almost all of you probably know the answer, but you're just not able to use the right words. Okay, fine. So, see, buckling strength, which material characteristic has the most significance as far as buckling resistance comes into picture? When you're talking about buckling resistance, which material property is important? You're talking about elastic buckling. So you're talking about, let's say, elasticity. Material property, can you tell me the parameter that represents elasticity?
Young's modulus.
Young's modulus, right? Elasticity modulus.
Yes, sir.
Axial rigidity.
Sorry, which one? Axial rigidity. Is that it?
Yes, sir.
EI value, sir.
Yeah. So axial rigidity is what? AE by L. So, or AE rather. So yeah. So AE or E. So what happens when the material yields? When I am at this point, what is my E value after I reach Fy?
0.
And my flexural buckling, what you typically know as buckling, strength, right? So I'm calling it P critical. What is it equal to as per Euler's buckling formula?
Y square EI by L square.
So buckling resistance was very high if it's a stub column, L is very small. Okay, this L value is very small, and as a result, your P critical is very high. So there is no risk of buckling for short column as long as you are in the elastic zone. But as soon as you reach the Fy value, okay, what happens to your E? It becomes how
It
much?
becomes 0.
Yeah. So after yield, after first yield, the elastic modulus becomes 0. So then your flexural buckling capacity suddenly becomes 0. So as soon as you reach Fy, then the member will buckle. Either it will buckle locally, or if you have a long member, slightly longer member, it may even buckle locally and globally. But it will be undergoing plasticization. Once the plasticization starts, then the members cannot take any compression. Okay, and that's where the fundamental difference between tension and compression arises. You might have heard of this phrase that tension is a stabilizing force, compression is a what kind of force? Tension is a stabilizing force and compression is a
Destabilize.
destabilizing force. Right? You understand why, right? Or from an example, at least you should understand. So if I have a rod and I'm applying tension on this one, okay, and what is the check for stability? How do we know that something is stable? If something is in a stable equilibrium, how do we know that?
Slope, maybe the.
So this is a hill, and there is a ball sitting on top of the hill. Is this a stable equilibrium or unstable equilibrium?
Unstable.
Unstable, sir.
How would we know that this is unstable?
It does not come back to its original position after it is disturbed.
Yes, so you have to disturb it. Very good. So if I disturb it, then whether it will come back to the original position or not. So in case of tension, what happens is that if I disturb this rod, so this is the straight rod and the forces are acting exactly aligned with the rod's direction. If I disturb this rod like so, and the forces are acting this, forces are still acting as they were acting before in tension, what will happen to the rod? Forces want the rod to become straight again. Correct? The forces are such that now these forces will form a couple. And if you look at this, the couple's direction, the force couple direction is in this direction. So these forces are forming a moment, net moment on the rod, so that the rod wants to come back to this original position. So if the rod rotates in this direction, it will come back to this position. And that's why we can say that tension is a stabilizing. Tension is a stabilizing force. You guys are following?
Yes, sir.
Yes,
Okay.
sir.
Now, if you look at compression, this is how the compression is acting. Okay. Now, if I create a disturbance here, I rotate the rod slightly from its perfectly straight aligned configuration, and compressive forces are still acting as they were acting before. Now, what are these forces trying to do to this rod? They are trying to, so the rod has already rotated from the original configuration, the rod already rotated by this much, and these external forces are trying to rotate it further in the same direction. Correct? The net effect of these forces as a moment is in this direction. So as a result, this is a destabilizing force, because if the disturbance is in this direction, then the external effect is also in the same direction. So it will not, the rod does not have any incentive to come back to the original position. So that's why this is destabilizing force. Destabilizing. Should it be BILI? Sure. Or BLI. Or this is stabilizing. What should be the spelling of bilizing?
BILISE.
EILI.
Okay. Fine. So that is the difference between tension and compression. Now, you know several examples, right? I mean, if you're riding a bicycle very fast, and then suddenly you have to apply a brake. Which brake is it safer to apply the brake? Which brake is safer to apply? Front one or the rear one?
Rear.
Rear
Rear
one.
one, right? All of you know that. And that is the same reason. So if you apply, imagine that this is a bicycle that you are riding. Where's the second wheel? Okay, somewhere here. Okay. And you are moving in this direction. And suddenly you apply the front brake. What will happen is that your inertial forces are acting. Inertial forces. So this is the direction of movement. I'm not showing that, but your inertial forces will be acting in this direction, and your friction will be, if I apply the brake suddenly, friction will be acting in this direction, which will be creating a destabilizing effect. Whereas, so basically what will it try to do is it will try to throw the cycle above the front one, and that's how the cycle can topple. On the other hand, if I apply the brakes here, then what do I have? I have a stabilizing effect, because now this wheel does not want to climb up. All it is, even though there is some rotatory force here, still the tendency is not that big. Okay. So as a result, you have a slightly stabilizing effect here, whereas in this case, when you are applying a force here, that was a destabilizing force. Okay. So that is why the fundamental difference between tension and compression exists. And because of that, once the yielding takes place, the elastic modulus is gone. And that is also in a way to say that pi square EI by L square, or EI, that is your flexural rigidity. So as soon as your E is gone, your EI is also gone. E is reduced to 0, your EI is reduced to 0. So if your EI is reduced to 0, then you don't have any flexural rigidity available. Then you don't have any buckling resistance available. And that's where immediately the buckling will happen. But we don't really call that buckling type of a failure, right? So this is an example. So even though this example is not from a column at ambient temperature, it is from a fire accident. But anyway, it shows the real picture. So you have a column. The column is loaded with gravity loads, and somehow the Fy decreased because of fire. And because of that, the column undergoes this kind of a local type of a buckling, which is basically a squashing kind of a failure. And that happened because of your decline in the E value. As soon as the yielding happened, the E value declined suddenly, and then this happened. Okay. Alternatively, what you can also have is a flexural mode. So a typical elastic flexural mode of buckling is relatively uncommon in civil engineering structures. Okay. So these pictures, nice pictures that you see, or in ASM you might have been taught, flexural buckling, right? So you have a straight column to start with, in boundary conditions, and then you apply a compressive force. And what do you expect? Say Fy is very large. There is no issue of yielding at any point, but still you can expect it to buckle. And what kind of shape typically you get as it buckles? For a simply supported beam, what would be the shape of this curve?
Y equal to A.
Sorry?
Pi by equation, sir.
Yeah, no, like it will be some commonly used function. That function is very commonly used.
Y equal to A
Sine
sin
function.
Sine function. The sine function, sir. Sine function.
Very good. Yeah, so it is supposed to be it is supposed to deform under a sine function, because if you use a sine function, it satisfies your equilibrium perfectly, right? So it is a sine function. A sine function looks like this, but typically, if you see a column really being tested in a lab, a typical column, you are not likely to see a sine function deformation. You are more likely to see a deformed shape that looks more like this. You have a sharper kink here, a sharper change of slope here, and other parts are relatively straighter, as you can see here in this example. So this is a simulation I have done of a beam or a column, you can say, and a compression is applied. At some point, it buckled. Okay. And also the flexural buckling also was accompanied by some local buckling and some yielding. And these are these effects, the local buckling and yielding, which make this failure, instead of a purely sinusoidal function, it makes it a more of a buckling. If we were calling it elastic buckling, then the shape should have been perfect sinusoidal wave. Okay, fine. So why does it happen that in real columns mostly we do not get pure elastic buckling, but we get something like inelastic buckling? Because real columns do not have the kind of slenderness wherein after a large deformation also you don't have any, your stresses do not exceed Fy. If you go for a very, very slender column, you know, like a spoke of a bicycle. Today's examples are all coming from bicycles. Spoke of a bicycle, you know, a wheel of the bicycle has, okay, good that I already have drawn a bicycle here, so I can very easily draw. You know what is a spoke, right? These wires, they connect the rim of the bicycle to rim of the wheel to the axle. So these spokes, these are thin wires, right? And if you compress them, they will buckle very easily, but there won't be any plasticity. As soon as you remove the load, they will go back to the original length. But typical steel columns that you see in buildings, etc., will not have that kind of a flexibility. They will, once they buckle, they will deform permanently. They will undergo some kind of a yielding, and that is because they are not as slender as that spoke that I was talking about, or as I spoke about. Okay, so there are two primary types of failures for columns or compression members that we come across. One is governed by squashing, and the other is governed by buckling. And then there are issues of local buckling. Okay, so squashing, I just explained to you, right? So as soon as squashing happens, then other types of bucklings happen, but then we don't call them buckling. So this kind of a failure, it's a squashing kind of failure, crushing type of failure. We don't call it a buckling failure, even though eventually there is buckling always. Even flexural buckling, when you see, most of the typical flexural bucklings are always combined with some yielding. So there is always some yielding here, and there is always some local buckling here. Okay, but we don't call them necessarily local buckling type of a failure or a yielding type of a failure, because it was triggered by flexural buckling. And for that, you need to do some calculations and see whether which one was the lower limit state, whether flexural buckling happened first or whether the yielding happened first. Okay, so then you may have a system which is undergoing flexural buckling, you may have a system which is undergoing torsional buckling, or you may have a system which is undergoing flexural-torsional buckling. Now, how many of you have heard of all these three terms? Flexural buckling, torsional buckling, and flexural-torsional buckling. No? Nobody?
Sir, we heard it, sir.
Okay. Okay, so you have heard of. Okay, how many of you can actually explain what is torsional buckling and what is flexural-torsional buckling? Okay, I mean, of course, you don't have the means to explain, because I mean, it's very difficult to explain in words. You probably need some kind of a drawing or something. But I hope some of you have basic understanding of what this type of buckling means. In ASM, I think flexural buckling has been covered, right?
Yes, sir.
Different types of boundary conditions: fixed, pin, fixed, and so on. Pin, and so on, right?
Yes, sir.
Fixed, free. Okay, so as I was explaining, this picture here, that one typically looks like a typical flexural buckling in minor axis or in weak axis. So weak axis and minor axis are just two words representing the same thing. So the beam is buckling or deforming in the weak axis. Okay, so this is the axis around which it has lower capacity. This one, the square shape, the cruciform cross section, if it is applied with axial compression or uniform compression, then you are likely to see this kind of a buckling mode, which is called torsional buckling. Okay, you can appreciate why it's being called torsion, because if you look at the centroid of the cross section, it is not moving anywhere. The centroid is sitting where it was sitting before, only it is rotating. Okay, and then each element is moving, but the movements are in such a way that the overall cross section is just rotating. This kind of a deformation, ignore this local buckling here. This, what you see here, this local waves forming, these are local buckling. Don't look into that, just ignore that. Now, if you look at the overall deformed shape of the beam, it is flexure very clearly, right? Does anybody doubt that it is flexure or not? Both the flanges are bending, right? So and both of them are bending in their in the overall cross sections weak axis. So this is flexure in weak axis. But also, if you look closely, you can see that one flange is bending more than the other flange. The top flange is bending more. Here you can see. Here you can see this is the deformation of this flange is more than the deformation of this flange. So at the ends, both of them have zero deformations, let's say, here and here. But somewhere in the middle, one flange deforms more than the other flange. What does that mean? That means that there is, in addition to the flexure, so flexure is making both of those flanges deform laterally or move laterally. But in addition to the flexure, you also have twisting. And because of the twisting, one flange is moving more than the other flange. And that's why this will be called flexural-torsional. This one will be called torsional. Sorry. This one will be called torsional. This is pure flexural. Okay. Now, which one happens in which case? Some explanations, some possible cases are discussed here. But let me go to the next slide. Here, this is a slide that is not there in your lecture notes. I have added it since it will be uploaded as a video also. So you can take a picture snap out here. Otherwise, I will also upload this revised PPT for me to copy. Okay. So what kind of cross sections do you see here? There are three categories I have created. Okay. Can anybody quickly tell me what is the first category? In this first category, you have two cross sections I have drawn. One is an I section, the other one is cruciform.
Doubly symmetric.
Symmetric about both axes.
Yes. The second one?
Symmetric about one axis.
Symmetric about one axis.
Correct. And the third one?
No symmetry.
Not
Not
symmetric.
symmetric.
No symmetric,
Yes.
asymmetric.
Correct. Very good. So this is called doubly symmetric. This is called singly symmetric. And this is called unsymmetric. Sorry. Okay. So now if you have doubly symmetric cross section, like this one or a pipe even, right? Circular pipe or even an elliptical pipe, then these kind of cross sections are likely to have, if you do the eigenvalue analysis, just like flexural buckling, if you do a more detailed three-dimensional eigenvalue analysis, what you will find is that it can have a flexural mode of buckling about x-axis. It can have a flexural mode of buckling about y-axis, and it can have a torsional mode of failure. And the three modes of failure are completely independent and they appear independently. So what you have to do is, let's say a beam is such a way that its flexural buckling capacity about y-axis, how much will that be against simply boundary conditions?
Pi square EI
Pi square AI
by
By L square, right? So let's say its IY is very low in comparison to IX. This one will be governed by IX. So IY is much smaller than IX. Then what will happen is, if you just use a beam of length L and apply compressive force, it will first buckle under flexure about y-axis. Okay, flexure about y-axis. That means weak axis buckling. Fine. Follow it. So this is the y-axis. About this, it will bend or it will buckle. That is first one. But somehow, if you can restrain that, so if you brace it laterally, don't let it move in that direction at all, then what will happen is that maybe this Ix will be exceeded, or pi square Ix divided by L square will be exceeded. So your P becomes larger than this value, pi square Ix by L square. When that happens, then it can undergo a buckling in such a way so that it is bending about x-axis. Okay. So the whole cross section, so right now the cross section is here, the top flange is here, it will move to somewhere here above it. likewise the entire cross section will move. So that will be called buckling about y-axis. Then if you restrain that one also, then maybe what will happen is there is something called, and torsion is a more complex phenomenon, and you will be it will be discussed in quite a bit of detail in the ASM course. What will happen is that there is a rotational constant that is often referred to as J, and also there is a warping effect, or referred to as IW or CW. There are various constants that are, okay, I can call it CW. So these two parameters, these are cross-sectional parameters. J, which is pure torsion, so you basically use G times J, and then I times CW. Sorry, E times CW. What am I saying? So warping is controlled by elastic modulus, and pure torsion is controlled by the shear modulus. So GJ or ECW or EIW, these two parameters control the torsion behavior of this section. And then similarly, you can just like here, pi square EI by L square, you can also derive an expression for torsional buckling of any cross section. And then when that value is exceeded, then the torsional buckling can happen. Now, there is no guarantee that your EY is the smallest and your combined coefficient that controls torsional buckling is the largest, and I-axis somewhere in between. It may be in any order, depends on the cross section and depends on how you define your X and Y. Okay, so in this particular case, your most likely chances are that your torsion will be happening first in this case, in this cruciform section. Torsion will be lowest, and then X and Y will be equal. Okay, so this is how these types of bucklings happen, and these are three independent type of bucklings. When you have a singly symmetric cross section, so you may have an example of an equal legged angle. So the two legs are of equal size. Then this axis is the axis of symmetry, and this axis is axis of asymmetry, passing through the centroid or the neutral axis. Okay. Similarly, you may have a channel section. In case of a channel section, this axis is the axis of symmetry. This one is the axis of symmetry, and this is the axis of asymmetry. You can have a T section, wherein you have the axis of, or an uneven or unequal flanged I section, where this is the axis of asymmetry, but this is the vertical one, is the axis of symmetry. So in all these columns, there are again three modes possible. Okay, why three modes possible? Because we are giving it only 3 degrees of freedom. There is a degree of freedom of lateral movement in this direction, lateral movement in this direction, and rotation. Therefore, 3 modes of failure, 3 modes of buckling. So the 3 modes of buckling are such that, and there will always be the higher order of these. So the first one will be the first half wave, then the second one can be of higher order. I'm not getting into those. You understand what I'm saying, right? So a column can have a flexural buckling. Column which was straight like this before, it can buckle in flexion like this, and then subsequently it can also buckle in flexion like this, in flexure only. But I'm not talking about that possibility. That is, of course, can be derived further from the first equations. I'm talking about the first 3, which are fundamentally different. So one mode of failure is pure flexure about the axis of asymmetry. So in this particular case of an angle, you can imagine if you apply compressive force, and the compressive force, the condition is that compressive force should be uniform. Okay, so it should be acting at the centroid. And if you do that, the angle will be buckling in such a way so that it is from this location, it will be moving to this location. Okay, or this location. So this one is pure flexure about the axis of asymmetry. But in addition to these, you can also have a condition wherein the column moves in the direction of this axis. But when it does that, let's say this one, okay, so from the original position of the angle, it moves to this location. But then along with that, there is also a twisting involved, and this can be derived mathematically. Of course, the objective of this course is not that. In that kind of a buckling, it will move in that direction, but also it will twist. Okay, and 2 such modes exist, wherein flexure about the axis of symmetry takes place, but also the torsion along with that takes place. So what we call them is when the flexure is coupled with one type of flexure is coupled with one type of torsion, we call it coupling, coupled modes. Okay, and there are two such modes that exist. Now, what is the difference between these two modes? Are these two modes identical necessarily? Anybody? So there are two modes where there is a coupling. That is, there is certain level of flexure and certain level of torsion. Now, all the two modes, the second and third mode that I've mentioned here, this and this, are they identical? Like once after the deformation, whether it's coupling in this mode or this mode, in both cases, the member will look exactly the same, or will it be deforming differently? People, no, so there is no reason to believe that, and you can see that actually this happens to be in such a way that they may not be exactly equal. What may happen is that in one case, you may have more flexure. So flexure can be represented as movement in this direction, right? Movement in this direction. So you can have more this much of flexure movement and a certain amount of rotation, twisting. And in the other case, you may have less flexure and more rotation. Okay, so they may be in different combinations, but these are still three fundamental modes of buckling, elastic buckling. Okay. And you can you have not taken the course in dynamics, but those who have may able to start appreciating what it means. So these will become the eigenvectors. How much it is moving in this direction and how much is moving in this direction. And the P critical that you get out of this analysis are the eigenvalues. Okay, so there will be one eigenvalue coming out of this, one eigenvalue for this, one eigenvalue for this. And for this, basically, you will get an eigenvector which is saying flexure in one direction, that is flexure in the axis of asymmetry, you have 1, and the other two directions, the movements are 0. So your eigenvector will be 1, 0, 0. In this particular case, you have 0, maybe, and then half and half. And in this particular, these are hypothetical numbers. I'm not giving exact numbers. We have not even defined a problem. It may be 3 by 4, 1 by 4, something like that. Okay, and these values can also be normalized. So there is no meaning of exact 3 by 4. It's not like their addition has to be equal to 1. You can choose them to be 1, or it can be anything. Okay, so this is how these buckling problems are solved, and I'm sure these will be solved in the ASM course soon. And then later on in dynamics also, you will learn this concept. So there is an eigenvector with each mode. So one eigenvalue that corresponds to each mode, and then there is an eigenvector that corresponds to that mode, which has, because there are total 3 modes possible, so you have 3 values for each mode. Okay, then you have another type of a cross section that may be completely unsymmetric about any axis. So you cannot find a single axis about which it is symmetric. And in such kind of a cross section, what you will have is a combination of deformations which form each buckling mode. So if you look at buckling mode 1, 2, and 3, both of them have a component of flexure about A axis. I have marked A axis like this and B axis like this. I did not mark them at diagonal axis directions in this case because there is no meaning. Here it was one of the diagonals was a symmetric, and that's why there was a meaning of doing it that way. Here none of the axes are the axis of symmetry, so it doesn't matter how I draw them. I can pick any axis I want. So flexure about A axis and flexure about B axis, B axis, and torsion. So all 3 are combined in all 3 modes. So all 3 modes will exist, but each mode will be a combination of movement or flexure in this direction, flexure in this direction, and a little bit of rotation. Only the proportions in which these movements happen in each mode will be changing. So in first mode, it will be different proportions. In the second mode, it will be different proportions. Third mode will be different proportions. Okay. So this is basically summary that you should learn in course ASM. I'm just teaching you a little bit sooner because we have to continue with this discussion. So what happens is that the Indian code does not even talk about this mode of failure at all. completely ignores it. This particular mode of failure, that is singly symmetric, it allows you to use the existing equations which exist for the. So let me retract. So for angles, it allows you to design the angle for a flexural torsional type of a buckling. That is, this is flexure about the axis of symmetry and torsion. So we'll call it flexural torsional. So angles, it allows you to design for flexural torsion. But all other channels and T, etc., it requires you to design as per flexure only. Even though these exist, these are a possibility of failure, it still requires you to design as if it is purely flexural. And of course, there is no equation available for purely torsion, because these kind of cross sections are not very common and they hardly ever govern the design requirement. For such kind of cross sections, only these two govern: flexure about x-axis and flexure about y-axis, for which provides you the most of the equations. Okay, fine. So out of these three are gone in the unsymmetric cross section mode. Unsymmetric type of cross sections. For singly symmetric, you have an equation for angles only, for flexural torsional, and then you, for other cross sections which come in under this category, you use equations which are meant for flexure. And then for flexural members, again, you use flexure about y-axis, x-axis, but you again don't, the code, Indian code does not give you the equation for the torsion. Okay, moving forward. So you may have flexural buckling, as I explained. You have torsional buckling, and you may have flexural torsional buckling. Okay. So either you may have a situation where only about one axis, that is weak axis, the symmetry exists, or there is no symmetry at all. Then you may have flexural torsional buckling. In addition to that, there are three factors which play a role. Okay. So this factor I briefly discussed here, because there is, in both these examples, in this example and this example, you can see that there is local buckling happening. There is local buckling happening, but these designs were not necessarily governed by local buckling. I'll talk about local buckling a little bit. Imperfections play a very important role. How do imperfections play a role? Imperfections affect the buckling capacity, because the Euler buckling equation that you have derived, pi square EI by L square, that is for what type of a column?
Right.
Perfect column.
Ideal columns.
Ideal columns. Yeah.
That is for a perfectly straight, concentrically loaded column. Right? So if any of those conditions change, if either the column is not loaded concentrically or if it is not straight to start with, then that equation does not hold true, and we will see how it is addressed. And then you have issues of residual stresses. Residual stresses also affect the column behavior, and we will look at it now. So residual stresses you already know. Imperfection also you understand, right? Most of you understand what imperfection means. Basically what imperfection means is that this is the column. This is the column that we wanted to design. But when you bought the column from the industry, from your supplier, you see that the column is not perfectly straight, and most of the columns are not perfectly straight. Usually the imperfection is taken, it is proportional to the length. But if you go for longer columns, you are more likely to have an imperfect column. And imperfection again is higher in the weak axis than in the strong axis. Okay, so most of the, let's say you buy an I section, you have a high chances that the I section, which has two flanges, on one on top, one on bottom, it will be going, and but after some time it will be bending slightly. So if you look at it by aligning it perfectly straight, you will see that there is a little bit of bend. Okay, so that is called imperfection in the column. Residual stresses you already know, and local buckling is basically when would the local buckling take place? Local buckling takes place when you have this elements, individual elements, which are elements of a column cross section. So you have an I section. It is made of three elements, two flanges and a web. So each element, that is, let's say the flange, if the flange thickness is very small in comparison to flange width, then it can undergo local buckling, and that is another factor that governs the behavior. Okay, so flexural buckling, you are all very well familiar with flexural buckling. Quickly recapping, so Euler buckling is Euler had basically derived the equations for buckling capacity of a column. That's why Euler buckling. It is known as Euler buckling, flexural buckling. I square EI by L square is the capacity of a simply supported column. You have a simply supported boundary conditions. Pin roller here, pinned here. P axial load is applied, deflected shape. And then if you change the boundary conditions, then the value of effective L changes. So you have to calculate a new L effective, which is also sometimes written as KL. So the K here becomes a factor that controls the effective length. So basically what you need to look for is the location of the point of inflection, where the curvature of the cross-section curvature of the member changes. So here up to this point, let's say up to this point, the curvature was in such a way that let's say from here to here, the curvature was such that it was in this direction. Okay, and from here to here, the overall curvature is such that it is in this direction. Okay, so this will be called the point of inflection, where the curvature is 0, and on one side it is positive, the other side it is negative, and the distance between the 2 points of inflections will be known as effective length. So if you substitute that length into KL, so for this particular case, your K will be equal to how much? 1/2. Likewise, in this particular case, what will be the K value? Right? This is one point of inflection, this is one point of inflection, this would be the other point of inflection. Yeah.
0.7, sir.
0.7. There are double curvature here. 0.35 almost, right? See, if this was the full length L, if this was L, then you would have had 0.7 here. But the full length is L here, so you will have 0.35 L. Agreed? Now, you must remember the values that were taught to you. So let's go through so this table I've taken from IS 800, what you see here, the diagrams. So for this particular column and this particular column, the IS 800 also says, so the theory also says that your effective length should be 2L, correct? Because here you can extend it to the other side and you can see that these are the two locations. These are the two locations where the zero moment exists. Similarly, you can extend this column. In this direction, it is already there. You extend it the other direction, and you will have locations of zero moment or zero curvature, and that's where you will have point of inflection. So therefore, 2L should be the value. This is a simply supported case. 1L should be the value. That is as per the theory. But now in this particular case, where you are supposed to have a fixed rotation is fixed, but the lateral movement is allowed. The theory says that if I extend it, I should get L on each side, L/2 on each side. So effective L should be, KL should be equal to L. But the code says it should be 1.2L. For this one, you know, it's a fixed pin boundary condition. What was the value of effective L?
0.70.
0.7. Approximately 0.7 L. But the code says it should be 0.8 L. In this case, what is the value of effective length?
0.5.
But the code, yeah, but the code says you take 30% larger value. Fine. So in these two cases, it is fine. But in these cases, in these three cases, the code asks you to revise the value. And it is revising the value to be on the more conservative side. And the reason primarily for that is that the code does not trust the amount of rotation, rigidity your rotational supports can provide. Sometimes your rotational supports are not able to provide a perfect rigidity. And as a consequence, your effective length will change, even though you are considering them to be a fixed boundary condition. That's why your effective K that is available to you as per the code is this one. So even if you see that the boundary condition is such that it is perfectly fixed, still you cannot take the theoretical value. You have to take slightly larger value. Fine. So this table 11 exists in IS 800. Yeah, this one, table 11. Okay. Moving forward. So now, what governs the column behavior in compression, failure behavior of a column. So as I had mentioned, there are two failure modes, two possible failure modes. One is squash and the other one is squash or crushing, and the other one is buckling, right? So imagine that on the horizontal axis, I am plotting and mapping the length of the member. So as the length of the member is increasing, the capacity of the column will be decreasing, right? And that we know from the buckling theory. So we know from the buckling theory is what we know from the buckling theory is elastic buckling theory. As the length is increasing, the expression pi square EI divided by L square has the terms of L square in the denominator, right? What that means is that if I plot that curve in that space, then this is how that curve will look like. Okay, this is 1 by L square or pi square EI by L square. You just have to scale the vertical axis in such a way that you get pi square EI by L square. And this is your P critical value. Fine. So that is this part of the curve. As the length is increasing, I'll talk about lambda in a minute. As the length is increasing, your buckling, elastic flexural buckling, that's how it will be governing the behavior. But at some point, what will happen is that as you keep reducing the length, the required load, so if I have a stub column, like a square one, okay, and I'm applying uniform compression on this, at some level of stress, what will happen is that this material will reach its yield stress. Okay, so it will not buckle. In order for us to make it buckle, the stress have to be very high because it is a very stocky shape. It is not a slender column. Alternatively, I can also have a slender column. Even this one doesn't look very slender, but you get the idea. So it would have been a possibility to make this column buckle. Okay, but making this column buckle is not possible at all. Or in other words, if you reduce the L too much, then the required P value to make it buckle is very high. So a very high level of P is required to make this kind of a column buckle. We can't do that. But what will happen still is that the column will still fail much sooner than that. And what will happen? You will reach a particular level which you can call Py, which is equal to Fy by A, the cross-section area multiplied by Fy. As soon as that is reached, the entire cross-section will yield. And when the entire cross-section yields, then you cannot apply any further load. It will buckle locally. So wherever, if this portion starts to yield, then it will bulge out like so because of yielding. Okay, and then it cannot resist any further load. So then you will end up with these two limits. One limit is given by yielding and the other limit is given by this buckling. This is in a way theoretical representation of the column behavior in compression or any member's behavior in compression. Okay, so this column buckling equation, that is P critical, you can call it PCR or PCC, that is equal to pi square EI by KL square. And if I divide it with A, the area of the cross section, then what do I get? I get PCC. Instead of that, I get FCC, that is stress, so uniform stress in the cross section. That will be equal to pi square EI divided by area. I have added area here. Now, if I divide the whole thing again with Fy, that is yield stress, so what I get, this is FCC, that is the stress level at which the column buckles versus the stress level at which the column yields. Okay, and that parameter will be equal to the same expression, this expression, divided by Fy. I've just added Fy in the denominator. Okay, then I can take I divided by A as given here and convert that to R, right? So square root of IA is equal to R. Square root of I divided by A is equal to R. So I get KL divided by R squared from here. So this is the new expression, FCC by Fy. And what we do is we call this one FCC by Fy as 1 by lambda square. Okay, or in other words, lambda is equal to square root of Fy by FCC. So if I may just write this FCC by Fy I square divided by L by R. Okay. If I call this by 1 by lambda square, FCC by Fy, then lambda will be equal to how much? Square root of Fy by E KL by pi R. Am I right? Did I make a mistake here, or does it look okay? Let me check in IS 800. So the lambda expression is given as, if I take KL by R outside and divide by pi, so KL by pi R, and multiplied by square root of Fy by E. Yeah. So that is my lambda value. Okay. This is my lambda value. This is known as slenderness as per the Indian code. Fine. Now in Indian code as well as some other international codes, you will often see KL by R also as slenderness. And it is important not to get confused. Okay, so KL by R works okay because it only accounts for the cross-section shape and length. So R basically accounts for the cross-section shape, L corresponds to length, and you take the ratio of the two, and of course the boundary condition effect. So you incorporate these three things, which basically tell you, if you know the KL by R value for a steel column, you can pretty much tell what is the likelihood of it buckling versus its yielding. Okay, so for a typical column, if I give you a KL by R of, let's say, 180, from experience you can tell that it is a very slender column. A KL by R, on the other hand, 30, is a stocky column or stuck column. Fine, but this kind of a benchmarking or this kind of a thumb ruling will fail if I change my material. So this works okay for up to 350 MPa steel. I'm talking about yield stress. Okay, but if I go to a yield stress of, let's say, 500 MPa, then this may not be the right appropriate way of saying. So a KL by R of, I mean, since I've taken a very broad range, then it may be okay, but then still you cannot make very exact deductions about this one. Then what, or if I go for an Fy of, let's say, 1500, I have another steel, very high strength steel, which gives me an Fy of 1500. Then I definitely cannot draw these conclusions. In that case, I have to go to this expression, wherein I also incorporate the effect of the material. So in addition to KL by R, see, pi is nothing, pi is just a constant, so ignore the pi. Earlier you had just KL by R, that is one type of slenderness, and this is another type of slenderness, which in addition to KL by R also includes the material effect. So depending on what is the ratio between E and Fy for this material, its lambda value will be determined. So a lambda is equal to 1 usually corresponds to what? If I take lambda is equal to 1, substitute it here, Fy by E is equal to pi square R square by K square L square. Okay, I take the E to the upper side. Okay, so that is basically pi square EI by L square divided by area. Okay, so if I take Fy by multiplied by A pi square EI by K square L square. Right? What does that mean? How did I get here? I got here when I substituted lambda is equal to 1. Okay. And what does it mean? What does this expression mean? Fya is equal to pi square EI by L square.
Buckling capacity is equals to yielding capacity.
Yes. So that means, where am I on this curve? On this curve, I'm right here. This is the buckling capacity. This is the yielding capacity. The two are meeting here. And that is where my lambda is equal to 1. So if your lambda is 0.1, from here you can figure out. So if your lambda, if this lambda, this particular lambda value, not KL by R, if your lambda is 0.1, then no matter which material you are talking about, what length you are talking about, or what dimensions you are talking about, as long as your lambda turns out to be 0.1, you can say it is a stocky column. And if your lambda turns out to be, let's say 6, 5 or something like that, okay, then you can say that it's a slender column. It is going to have a buckling mode of a failure, and a lambda of 0.1 corresponds to something like a crushing kind of a failure, or yielding type of a failure. Fine. Anything in between? We cannot necessarily say that if you are exactly at, let's say, 0.95 of lambda, it is a yielding type of failure. We cannot say that, even though this expression suggests so, that up to 1, that is the behavior, and exactly after 1, suddenly you start having that kind of a drop. It doesn't really work that way. And that's why I'm calling this as the theoretical capacity. But the real behavior is not really like this. The real behavior is somewhat like this. Excuse me again for a not very accurate drawing. Okay. Can anybody tell me what could be the reason for that?
Maybe imperfections or experimental.
Yeah, experimental is not a good enough reason. Yeah, residual stresses and imperfections. These are the two primary reasons why you have to deviate away from this curve. This curve is deviating away from the perfect curve or theoretical curve in this region, primarily because of the residual stresses in this region. And in this region, it is deviating away from here primarily because of imperfections. The imperfections have a more important role in this region, and residual stresses have more important role in this region. Okay. So I think I'll talk about the effect of residual stresses in the next class. Maybe. How much time do I have? Oh, I have 15 minutes. Okay, fine. I'll carry on. Any questions? Today I did not stop for questions in the middle. Any questions?
So, so you told that when E becomes 0, my Fy will be at the yield point, my E becomes 0, and post that my column will buckle.
Yes.
Correct. But usually in the column buckling doesn't mean like yielding needs to be reached or something like that. So it can always buckle before yield point also, right?
Yes. So that buckling, strictly speaking, is known as elastic buckling. The buckling that you are talking about, that the column did not yield when it buckles, that is absolutely correct. So if it buckles in elastic mode, that's when you would have, you call it elastic buckling. And that is what typically we know as Euler buckling, elastic buckling. But there is no other word for what I wanted to describe. So that's why I had to use the word buckling. The more accurate way of explaining that would have been inelastic buckling. See, so for example, you have a liquid and you apply compression on it. The liquid simply moves away when you apply compressive load on it, right? So that is the similar way the metal behaves when it has plasticized. You apply the stress, it has zero stiffness, it simply moves away. Okay, and so therefore it, as you can see in this picture, first one at the top, the column, actually, what would you call it? I mean, I'm just calling it buckling because that's how it looks like. It is the local buckling. It's not a global buckling by any means. Okay, This one is more of a global buckling. This is more of a global buckling. This, even before it had locally, it might have been a global flexural buckling. But eventually, for most of the practical columns, after global buckling has kicked in, now the column is going to buckle. At that time, the stresses also is to start rising very quickly, and there will be some local buckling or some kind of a yielding accompanied with that. So even in this case, it happened because of yielding. This is not a buckling type of failure in strict sense. So it happened because of squashing. This is squashing kind of a failure. But even that, when you see visually, it looks like there is some level of buckling going on. That is local buckling. Okay. As I gave you the example of, let's say, the steel plates, these are made of fluidic material. So it just flows. As you apply the load, it just moves out of the way, like it's made of curtain or something, like a fabric or something. Has no compressive strength. Okay, I hope I answered the question. So if somebody just talks about buckling, yes, they are talking about elastic buckling. You cannot use this mode as elastic buckling. But if you want to explain what happens after yielding, even that is some type of a buckling.
So these things, what it is forming is called as a plastic hinge, right? If I'm not wrong.
Plastic hinge is a slightly different notion. See, plastic hinge, I mean, you can call it plastic hinge also, there is no harm. But typically plastic hinges, when this terminology is used, it is used, first of all, in a bending moment kind of a context. Hardly ever you use a plastic hinge in an axial load kind of a context. And that too, you insist on it remaining, plastic hinges are effective only when they remain unbuckled. So they yield, but they don't buckle. So your yield strain has to be limited so that beyond, up to a yield strain, certain level of yield strain, it won't buckle completely. So up to that level you can use, and that you can call it plastic hinge. So I would not call these as a plastic hinge. As I mentioned, plastic hinges are typically used in flexural context.
Okay, so got it.
Yeah, anybody else? What is the time? It's 46 already, right? So I still have 5 minutes maybe. You don't have a class after this, or do you?
We have, so.
You have, okay.
Yes, sir.
Okay, fine. So basically, as I was talking about, there are two factors that have three factors rather: residual stress, imperfections, and local buckling. So the residual stresses, basically, as I was in the very beginning, I was saying that if I take a column like this one, stub column, not a long column, very short column, and apply compression on it, and I make sure that the stresses everywhere are uniform. Throughout the cross section, the stresses are uniform, apply compression, you will see a behavior somewhat like this. And if I had taken a coupon and applied compression, let's say compression coupon, instead of a dog bone shape compression coupon, I make a cube shaped coupon, apply compression, the behavior would have been this one. Okay, elastic and then plastic. But if I take a column cross section and I apply compression on this one, the behavior will not be exactly like this. Okay, it will be different from this. And the reason for that is residual stresses. Okay, but what is happening is that the column already has some stresses somewhere, some locked in stresses. And as we are applying stresses from outside, those stresses start increasing and the entire cross section does not yield at the same time. Whereas in case of a coupon, which is much smaller, maybe cut from a small portion of the flange from here, that kind of a coupon, when you compress it, the entire cross section stays in elastic range for a while, and once it starts to yield, the entire cross section of this coupon yields together and then moves to plastic range. But in case of a column, that doesn't happen. Why does it not happen? Because you have residual stresses, and residual stresses, to start with, let's say you have, I'm looking at a flange, so at the corners of the flange you have in the middle you have tension, right?
Yes, sir.
Yeah, so at the corners you have compression, in the middle you have tension, and then at that time the net stresses are zero. There are no net stresses and you are not applying any axial force at the column at the time. Then you start increasing the axial force on the column, then all the stresses start increasing. So all the compressive stresses start increasing and all the tensile stresses start decreasing. So this area starts decreasing and this stress values, they start increasing. So what will happen now is as you keep increasing your force, axial force, some fibers will start reaching the yield point. Okay, but not all fibers. So not the entire cross section is reaching the yield point. Even sooner than that. So let's say this stress was Fy by 3, 1/3 of the Fy value. So up to 2/3 of the Fy you can push, but when you are only 1/3 of the Fy away, sigma y away from the yield point, this particular fiber, which was already at 0.3 or 0.33 Fy, it can take only 2/3 of the Fy further. So it will go up to here. Sorry. It will go up to this point, and beyond that, it will yield. As soon as this fiber yields, what happens to its E value? This fiber's E value, as soon as it yields?
0.
0,
0.
right?
0, sir.
Correct. So this fiber yields, its elastic modulus becomes 0, but all these fibers have not yielded, and their E values are still same as before. And as you push further and further, more and more of the cross section yields, and more fibers start reaching the yield stress value, or their elastic modulus starts declining. As a result, your effective E value of the cross section also decreases. When you are calculating the flexural strength, flexural buckling strength, you are calculating pi square EI by L square, right? So that E value is changing, effective E of the cross section. As more and more fibers are yielding, your E is changing, okay? And slowly, gradually, you are turning into the entire cross section yielding, and when you have 0 E. So as a result, what will happen is that if the entire cross section were to yield together, you would have followed this curve. But since some fibers are going to start yielding sooner, they will not be contributing towards the stiffness. Slope of this line is the stiffness. So your stiffness is starting to decline as soon as the extreme fibers start to yield. The fibers that were carrying the largest compressive residual stress. As soon as they start to yield, your slope of this axial strain versus axial stress plot starts to decline. So a coupon may behave this way, but a step column will behave this way. Okay, it will be a more gradual change. Now that will have a role to play in the capacity. So what will happen is that at that point, let's say when the load is at this level, okay, your net E of the cross section is not as same as the original E. It is a reduced E value. Okay, and for that reduced E value, if you calculate your buckling strength, what will it be? Pi square EI by L square, but that is the reduced E, because the fibers which have already yielded are not going to contribute towards the flexural rigidity, that is EI. Right? So therefore, you will have a reduced capacity. So in the next class, I will talk about the theory of tangent modulus. I'll stop here today. Okay. Any questions? Were you able to follow at least a little bit how the residual stresses affect the column capacity?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Yes, sir.
Yeah. So basically what I'm trying to say is that if it is a stub column, eventually it will offer the full resistance that a coupon was resisting. So it will still resist F sigma y A. Okay. Because after some strain, it will reach that value. For a step column, it does not affect it completely. But a column that is somewhere with a slight amount of slenderness, there it will start to play a role. That we will explain in the next class. Okay. Any questions?
Sir, in comparison, we looked at coupon behavior and the member behaviors, right,
Yeah.
sir? But in
Yeah.
tension also,
Yeah.
there will be one coupon and there will be one, if you take one in the column, there will be some residual stresses.
Yes.
So in tension, will it be, residual
Very good
stress?
question. Very good question, Lohit. Please remember to ask this in the next class.
Okay,
I think
sir.
I'll be better placed to answer that.
Yes, sir. Yes,
I have
sir.
not covered some topic now, so that once we cover that, I think we'll be better to understand that.
Sure, sir. Thank you, sir.
Any other questions?
So I have one of the questions from the previous class, the topic of the previous class.
Yeah.
You said that for like when we are doing the shear lag test for like I sections and all, we need to take some specialized literature.
Shear lag, designing for shear lag.
Yes, sir. For
Yes.
she like for other sections apart from single angles.
Yes.
But in the section 6.3.4 in the code, it says that the rupture strength TDN of the double angle I sections and other rolls.
Okay. Okay. Maybe I might have missed that. Section
3.4, sir.
Okay. The rupture strength of the double angle channels, I sections and other road sections connected by one or more elements to and at that will also govern by shear lag effect, the design and strength of such sections. Okay, yeah, fine. So yeah, it gives you the beta value. Basically, this is the factor for beta factor that I was thinking is probably not available, but it gives you the beta value. We'll have to see how accurate it is and how many cases it covers. Yeah, thank you for pointing that out.
Thank you, sir.
Yeah.
Sir, in the same way from the previous lectures, tension members in the example 3. So when the area, I mean, there was given a gross area, but in the gross area, bolt area, I mean, whole area has been detected.
Yeah, actually, the thing is that I have referred to several textbooks. Sometimes they take the gross area as the gross area. Sometimes they deduct that area from the, because the fracture path has to follow that. There is no single strict rule. You refer to one textbook and you can follow that.
I mean, what do you suggest? I mean, should we detect it or?
I mean, I have followed in that example. I have deducted it, I think.
Okay. Okay. Thank you.
Yeah, you can follow any convention. Anything else? Okay, then let's call it a day. Thank you.
Thank you.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.